Alright, so today we're going to be exploring the concept of linear momentum, which will be especially useful when we solve questions on collisions. So consider two blocks, block 1 and block 2, which are moving toward one another. We let the velocity of block 1 be v1 and the velocity of block 2 be v2. v1 and v2 are vectors, so at some point of time they will collide and they will exert forces on one another. So let us analyze the forces which each block experiences individually. So if we consider block 2, there is a force exerted by block 1 on block 2. So we will call that force F12, and that force acts towards the right. So similarly, if we consider block 1, there is a force exerted by block 2 on block 1. So by Newton's third law, you should be able to tell me that F21 equals to F12 magnitude wise. Because the law also tells us that they must be opposite in direction, so we know that F12 equals negative F21. Again, being mindful that all of these are vectors. Okay, so F12 is negative F21. So with this information, we can take it a step further by adding F21 on both sides, and we will get F12 plus F21 equals to 0. So if we consider block 1 and block 2 as the system, we note that there is no net external force acting on the system. So if we take a look at this equation, the forces only involve block 1 and block 2. They are only exerted by block 1 and block 2 on block 1 or block 2. So therefore, F12 and F21 are both internal forces. So internal forces are forces which are exerted by objects within the system on objects which are also within the system. So as you can see here. So there is no net external force acting on the system. It's an isolated system. So we can change force to mass times acceleration, as we all know. So being very careful, since this is the force by 1 on 2, so it should be the mass of 2 times the acceleration of 2. Similarly, F21, so it should be M1A1 equals to 0. And furthermore, we know that acceleration is the rate of change of velocity. So we can change A2 to dv2 dt and A1 to dv1 dt. Doing a bit of manipulation, since M1 and M2 are both constants, so they can be brought into here, and we can combine the two terms, since it's both d dt, and we will get this expression. So we know that momentum, which is given the symbol P, not MP, momentum is mass times velocity. So we can change M1 V1 to P1, the momentum of block 1, and we can change M2 V2 to P2, which is the momentum of block 2. So take note here that momentum is a vector which will follow the direction of the velocity vector. So if the velocity vector points towards the right, then the momentum vector also points towards the right. So from this expression, we see that d dt of this whole thing equals to 0. So this tells us that P1 plus P2 does not change with time. So in other words, it remains constant before, during, and after the collision. And this brings us to the principle of conservation of momentum, which states that the total momentum in an isolated system will remain constant with time. So just to reiterate, isolated means that there is no net external force acting on the system. So let's consider these two blocks. We have ball 1 and ball 2. Ball 1 has a larger mass than ball 2, but both of them have the same velocity. So can you tell me which ball has a greater momentum? Yes, so ball 1 has a greater momentum than ball 2 despite the fact that they both have the same velocity. So let's consider ball 3 and ball 4, which both have the same mass, but ball 3 is moving with a greater velocity than ball 4. So we can say that ball 3 has a greater momentum than ball 4, right? And this is despite the fact that both of them have the same mass. Let us consider an additional ball, ball 5, which is moving toward the left. So what can we say about ball 5's momentum? Noting that momentum is a vector, we can see that the momentum of ball 5 is opposite in direction to balls 1, 2, 3, and 4. So noting the direction of the vectors is important, especially when we are going to solve problems later on. And we need to put in the correct signs in the equations. Right, so now we have a review question. An astronaut is a short distance away from her space station without a tether rope. She has a large wrench. What should she do with the wrench to move toward the space station? And we have options A through E. Okay, so we will consider the astronaut and the wrench as the system. So if we consider the initial momentum, we should note that it is 0 because both the astronaut and the wrench are not moving. Right? So the initial momentum is 0, and what we want to happen is for the astronaut to move toward the space station. So let's say this is the space station. So if we want the astronaut to move towards the right, where should the wrench, how should the wrench move? So you should be able to tell me that the wrench should be thrown away from the space station. So this is the only way where the conservation of momentum will hold. Right, since this is an isolated system, there are no net external forces acting on the astronaut wrench system. If we want the astronaut to move toward the right, and the wrench is also moving toward the right, then the initial momentum will not be equal to the final momentum because there is some gain in momentum toward the right, which is not what we want. So we need the wrench to move towards the left, right, to balance out the momentum of the astronaut moving towards the right, towards the space station. So this way the final momentum will also be 0. So next we have another question. A basketball is tossed up into the air, falls freely, and bounces from the wooden floor. From the moment after the player releases it until the ball reaches the top of its bounce, what is the smallest system for which momentum is conserved? Right, so we note that the question is asking which system is momentum conserved. So we recall that for momentum to be conserved, there must be no net external force acting on the system. So furthermore, they are asking for after the player releases the ball up until it reaches the highest point of its bounce. So actually the player is out of the question, because we are only considering the moment after the player releases the ball. So the answer should actually be D, the system of the ball plus the earth. So right after the basketball is released, up until it rebounds and reaches its highest point, we note that there is only one force acting on the basketball, and that force is the force of gravity. The force of gravity. So if we consider Newton's third law, if the earth exerts a force on the basketball also exerts an equal and opposite force on the earth. Yes, so these two forces are Newton's third law action-reaction pairs. Right, so if we consider the ball-earth system, then the force of gravity will be an internal force. Hence, there is no net external force acting on the ball-earth system, and momentum is conserved. So if you consider any other option, there will be an external force acting on the system. Yeah, so for example, if you consider option A for the ball, there is a net force acting on the ball, which is the force of gravity. Same for the ball plus the player, the ball plus the floor. So we can actually classify collisions into a few types. And to do so, we can ask ourselves a series of questions to classify them. So we first ask if the collision is happening in an isolated system. If it is happening in an isolated system, then momentum will be conserved. However, if the system is not isolated, then momentum is not conserved. And we will need to use the impulse momentum theorem to help us. Next, we ask ourselves whether the total kinetic energy is conserved. If the total kinetic energy is conserved, then the collision is elastic, and we can use this equation, which we will derive later, U1 minus U2 equals V2 minus V1, to help us solve problems. If kinetic energy is not conserved, the collision could be perfectly inelastic. A collision that is perfectly inelastic will result in the two objects sticking together after the collision and moving off as one. They coalesce. The collision could also be inelastic, in that there is a loss in kinetic energy, but there is no coalescence. So let us first consider elastic collisions. So before the collision, let's say there are two masses, mass 1 and mass 2. We let the velocity of mass 1 be u1 before the collision. The velocity of m2 before the collision is u2. We can calculate the total momentum of the system before the collision. So Pi equals m1u1 plus m2u2. Similarly, we can also get an expression for the total kinetic energy before the collision, which will be half m1u1 square plus half m2u2 square. After the collision, we let the velocity of mass 1 be v1 and the velocity of mass 2 be v2. So for this convention, we let velocities before the collision be denoted by the letter u, and we let velocities after the collision be denoted by the letter v. So similarly, we can write out expressions for the total momentum and total kinetic energy after the collision, which will look very similar. It's just replacing the u by v. We know that momentum is conserved for this system since there are no net external forces acting on the system. So what we can do is we can equate the initial momentum, which is the momentum before the collision, to the final momentum, which is the momentum after the collision. So we're going to do a bit of manipulation. So what we can do is we can move all the terms involving m1 to the left side, and we can move all the terms involving m2 to the right side. Next, we can factor out the masses m1 and m2 to get this expression. And we can remove the vector notation if we let signs represent the direction. So we can take one side. We can take the right side, for example, to be positive. So if the velocity points towards the left, then it will be negative. So to give an example, let's say v2 points towards the left and has a magnitude of 3. So for v2, we will substitute in negative 3. We know that for an elastic collision, kinetic energy is conserved. So we can equate the kinetic energy before the collision to the kinetic energy after the collision. So we will get this expression. So you can see that there's a half that is present throughout the equation. So we can multiply that out and we're left with this expression. So we're going to do the same thing. We're going to move all the terms with m1 to one side and all the terms with m2 to the other side. Then we're going to factor out m1 and m2. And now you can see that if you take a look at these two terms, we have u1 something square minus something square. This one also something square minus something square. So we can actually use the difference of two squares formula, which is a square minus b square equals to a plus b, a minus b. So we can actually get this expression. So u1 square minus v1 square equals u1 plus v1, u1 minus v1. Same thing for this. So what we can do next is we can take this equation and we let it be divided by this equation. Right, so this divide by this and this divide by this. So you can see that the masses cancel out as well as this term on this side cancel out, also this term. So we are left with this expression. This is what's left. So doing a bit of rearrangement, we will get u1 minus u2 equals v2 minus v1. And this is known as the relative velocity formula. So what's happening here is that the relative velocity of approach is equal to the negative of the relative velocity of separation. So if you consider the relative velocity before the collision, let's say we take the perspective of mass 1, so it'll be u21 equals negative v21. So this is u2 minus u1 equals to the negative of v2 minus v1. So these are the speeds of mass 2 with respect to mass 1. If we take the perspective of mass 1, so if we bring over the minus sign, if we apply the minus sign to the left side, we will get u1 minus u2 equals v2 minus v1. So it's the same as this. So next we consider perfectly inelastic collisions. So simply we set up the problem, and the total initial momentum is m1 u1 plus m2 u2. However, after the collision, two masses coalesce and move off as one, so we give them a common velocity of v. So there's no need for v1 and v2. So the total final momentum will be m1 plus m2 times v. So we treat m1 plus m2 as one object since they coalesce. Using the conservation of momentum, we can just take this and equate this to this. Take note that kinetic energy is not conserved for perfectly inelastic collision, so do not try to equate the total initial kinetic energy and the total final kinetic energy. So we have another review question. A bomb initially at rest explodes into several pieces. Is linear momentum of the system, the bomb before the explosion, the pieces after the explosion, conserved? Explain. So if we consider the bomb before it explodes, right, there are no net external forces acting on the bomb, so it is an isolated system and momentum must be conserved. Right, so after the bomb goes off, the fragments will go off in many different directions. So if you consider the vector sum of the momenta of all the different fragments after the explosion, then they will add up to 0 vectorially. So this is how momentum is conserved. So is kinetic energy of the system conserved? Explain. Okay, so there is actually a transfer, or rather a conversion of energy. So the chemical potential energy of the bomb is converted to kinetic energy. Okay, so kinetic energy is not conserved. Basically, before the bomb explodes, there is no Ke. After the bomb explodes, there is a lot of Ke. Suddenly, the pieces of the bomb can move off in different directions. An open box slides across a frictionless icy surface of a frozen lake. What happens to the speed of the box as water from a rain shower falls vertically downward into the box? So basically, as time passes, the box will collect more and more rain, and the box will get heavier and heavier. Right, so the mass of the box will increase. So if we consider the horizontal direction, which is the direction in which the box is moving, we see that there is no net external force acting on the box. So this is an isolated system and momentum should be conserved. So we let the mass of the box be m without any rain, and it's moving at a certain velocity at the start. So the initial momentum is mass times velocity in the horizontal direction. Yeah, so we do not have to account for the rain since it falls vertically. As time passes, the mass of the box will actually increase, and we want to find out the final velocity. So the final momentum will be m plus m v prime. We know that the initial momentum must equal to the final momentum. So we see that final velocity will actually be m over m plus m times the initial velocity. So basically this expression will give you a number that is less than 1. So basically the final velocity will be less than the initial velocity. Okay, so the speed will decrease. So next we discuss about the impulse momentum theorem. So this is for the case if momentum is not conserved, so which is to say that there is a net external force acting on the system, causing its momentum to change. You know from Newton's second law that the net force will be equal to the rate of change of momentum. So if we integrate both sides with respect to t, and we put in some limits, so we consider initial momentum, final momentum, and initial time, final time. So at time ti there is momentum pi, at time tf there's momentum pf. Then if you integrate 1, it's just p, and then you get pf minus pi. The left hand side stays the same. And final momentum minus initial momentum is actually the change in momentum. Right, and this expression is actually defined as impulse. This expression is defined as impulse. And this expression you can interpret it as the area under the graph of the net force against time. Area under graph of net force against time. And you equal the change in momentum. So if I were to give you a graph with the y-axis being net force and the x-axis being time t, then if we find the area under the graph for a time interval, that will give us the change in momentum for that time interval. So if net force is constant, then you can just reduce it to net force times t equals to the change in momentum. So let's consider two balls, a bowling ball and a golf ball. So they are both moving at the same velocity v. Let's say I want both bowling balls to come to a stop. So to do that, I apply the same constant force F to both balls. So can you tell me which ball will take a longer time to stop? Yeah, so the bowling ball should take a longer time to stop. So if we consider the impulse momentum theorem, we are applying the same force on both balls, but take note that the bowling ball requires a larger change in momentum than the golf ball. So this basically we want it to come to a stop, so we want the momentum for the bowling ball to change from mv to 0. For the golf ball, we only need to change from small mv to 0. Alright, so the change in momentum is greater for the bowling ball. Consequently, for the same force applied, it requires a larger time to come to a stop. So this is consistent with our everyday experience. So similarly, if let's say I were to want both balls to come to a complete stop in the same amount of time, then can you tell me which ball requires a larger force for this to happen? Yes, so the bowling ball requires a larger force if you want both balls to stop at the same time, after the force is applied for the same amount of time. So again, the change in momentum for the bowling ball is greater than the change in momentum for the golf ball. If you want the time over which the force acts to be the same, then the force applied for the bowling ball must be greater than for the golf ball. So we have another review question. A massive tractor is rolling down a country road. In a perfectly inelastic collision, a small sports car runs into the machine from behind. Which vehicle experiences a great change in momentum of larger magnitude? Okay, so we consider that this is a collision. Since there are no external forces acting on the tractor sports car system, so it's an isolated system. When they collide, they will exert forces on one another. And by Newton's third law, these forces must be equal in magnitude. Yeah, the forces must be equal in magnitude. So we note that F delta T is change in momentum. Yeah, so now we are considering the case for either object. So don't get confused. So this change in momentum is for either object. If we consider each object, there is a net force acting on it. It is only when we consider both objects as a system that there is no net force acting on it. Alright, so the net force acting on either object should be the same by Newton's third law. We also note that since it is the same collision, so the time of impact should be the same, the time over which the force acts should be the same. So we can see that F and delta T is the same for both objects. So the change in momentum for both objects should be of the same magnitude. Next, two students hold a large bed sheet vertically between them. A third student, who happens to be the star pitcher on the school baseball team, throws a raw egg at the center of the sheet. Explain why the egg does not break when it hits the sheet, regardless of its initial speed. Okay, so if we were to compare if you throw an egg against a wall versus if you throw an egg against a bed sheet, what is the difference? Right, so let's say in both situations they have the same initial velocity. It's the same egg, so it's the same mass. So the egg has a momentum of mv in both cases. And basically when you throw an egg against a surface, the surface will exert a force on the egg to cause it to come to a complete stop. If you don't believe me, you can try to throw an egg against the wall. So you want mv to go to 0, similarly mv to go to 0. So the change in momentum in both cases is the same. So what is the difference? Actually, the difference is the time interval over which the egg is stopped. So for the sheet, you can actually try this yourself. If you throw an egg against the sheet will take a long time to stop the egg. Actually, the sheet will deform, and the force and the time over which the force exerted is very long. So this is very different from if you were to throw an egg against a wall, in which the time interval over which the egg is stopped by the wall is very short. So by the impulse momentum theorem, for the same change in momentum, if the time interval over which the force x is larger, then the average force will be less. The average force will be lower.